Alright, time for another DraftPhysics.com video presentation. DebatePhysics.com also, and so we do have a little debate in the comment section. So I will attempt to address it more completely. Alright, so I did find this raphaelhythloday guy. It was in the, the whatever held for review folder for whatever reason. So anyway, and so we'll have to argue the Newtonian quote, which I think I can do now. Okay, trying to illustrate it did work. Anyway, okay. I bring the quote to illustrate the meaning behind his corollary 3. So again, you're stating the meaning. A corollary, a proposition that follows from and is often amended to the already proven. Okay, so I don't know if what's, whatever axiom, whatever words you want to use for something he's established, and then he goes further and explains what he's established, but I don't think that's it anyway. I am illustrating that Newton had no issue taking the difference of contrary motions to maintain a quantity of motion. Yeah, the point was he did it to maintain it. So he always conserved the motion, and he's basically in the first sentence describing how a system internally can't do anything but always have the same momentum in it. So he's basically saying quite overtly that you can't make it hit light things and create more energy by moving light things faster. Okay, you can't make more momentum. So the first proposition is without an external force interfering, whatever force is in a section of space, and you don't allow anything into that section, whatever happens in that section, you will always conserve the momentum. So again, he's arguing directly against Leibniz in stating that momentum is conserved, not mv squared, momentum, mv, that's conserved. And it is Newton who you claim to support your reasoning. I don't claim that Newton supports me, and I don't claim that I support Newton. I'm saying that I agree with Newton, okay, about what the conserved entity in reality is. I also believe, like he did, in three-dimensional real space, and that all you have is Galilean relativity. You don't have any Einsteinian one. That things are real, and they're moving in real three-dimensional space by a function called time, not a dimension called time, a function called time. All right, you must reconcile his two statements. So the fact is they aren't in conflict. Okay, so that's what I will demonstrate. So I don't have to reconcile them after all. Okay, even though I would say the second statement is mushy. Okay, it can be understood to be not in conflict with what he previously stated, which is you always have to conserve the momentum, is what he's really saying. He's saying quite clearly, you can't finagle, nature can't finagle momentum, rather than argue one or the other. Well, I think it's fair when there are two quotes from somebody like even Einstein to have a disagreement about, which one is more legitimate, which one did he say with more veracity, or which one came later, or to make those kind of arguments. Clearly, the statement about, 1 unit of force equals 1 unit of momentum, clearly that statement was made earlier in his thesis, and so you would argue it has higher standing. Okay, with regards to the bulletproof spring, so that we'll get to later. So let's do the argument from Newton's conflicting statements, where I guess I'll have to read from Newton, which I really don't want to do. All right, so this is the relevant corollary, and so part of what he's saying here, like I guess it's worth just stating that he's talking about his closed system and the idea that without an external force, nothing can happen that changes the amount of momentum that's happening to the object. It always has the same momentum. So it's the quantity of motion, which is collected by taking the sum of the motions directed towards the same parts. So it's internal. That's what he means by that. And the difference of those that are directed to contrary parts, just meaning stuff internally suffers no change from the action of the bodies among themselves. So anything I put in a closed system where I don't allow something else to interfere with it, everything that happens in there has to equal the same total. All right, for action and its opposite reaction are equal. So again, he's stating that anything that happens has to always end up with the same total. All right, by law 3 and therefore by law 2, they produce in the motions equal changes towards opposite parts. So whatever's going in any direction always adds, in the sense that if something is going to go in an opposite direction without an action to cause it to do that, then that has to come from something. You have to account for where it came from. Therefore, if the motions are directed towards the same parts, whenever is added to the motion of the preceding body will be subtracted from the motion of that which follows. So he's just arguing that whenever two things interact, one of them's going to lose energy, one of them's going to gain it, or vice versa. What's really happening is that the two bodies are going to exchange their state, and the total state will always be the same number. Okay, so one can be an 8 and one will be a 2, or one of them can be a 5 and a 5, or one of them could be a 4 and a 6. You can just make up numbers for the quantities that they'll contain, but they have to contain this total. So that the sum will be the same as before. So he's basically making a conservation of momentum argument, and clearly he believes in momentum. If the bodies meet with contrary motions, there will be an equal deduction from the motions of both. Okay, so if they have opposite motions, you're still going to end up with the same total coming out. So 2 arrows go in, 2 arrows will come out, and those 2 arrows have to equal the 2 arrows that went in. Not complicated. And therefore, the difference of the motions directed towards opposite parts will remain the same. Okay, thus, if a spherical body A, so this is where I start drawing, with 2 parts of velocity is triple a spherical body B. So he's just basically doing the 1 to 3 thing. All right. So we have a pendulum, we have a 1 mass, and we have a heavier 3 mass. Now the problem is he has these both going in the same direction. So as he'll state here, he's going to give them velocities. So we have a 1 mass and a 3 mass. A is the 3 mass. Okay. In the same right line with 10 parts. So A has 2 parts of velocity. So it's going 2 velocity, 2 miles an hour. B is going 10 miles per hour. Okay. So that's the difference. And B is much lighter than A. And so B is going to essentially combine its energy with A in some way. Now, this is the part where I would argue Newton is not paying any attention to a real experiment. He's just talking about theoretically, okay, in some idealization. There's no relevance to an actual elastic or inelastic. There's no connection to anything real, because what he's going to recite is basically impossible. You can't make it happen with any device that we have. So he's just describing exchanges between these two entities that have a quantity of motion. All right. Okay. The motion of A will be that of B to 6 to 10. So the argument is, we'll move to the drawing temporarily, and we can always put this back. All right. So here's the illustration of it. Ugh. Okay. Yeah. Sorry, cameras. I don't know why it does. This is getting, it's more angled than it really should be. Anyway, I have to work on that. All right, so you have the B is the 10 velocity, 1 mass. You have A, the 2 velocity, 3 mass, and they're going in the same direction. So the argument is that this has 6 momentums, and this has 10 momentums. All right, so you have a total of 16. And you're always going to have this total of 16. So no matter what happens in the interactions between these two bodies, you're going to have to keep this 16. Now he theorizes that, okay, B collides with A, and gives it 2 parts or 4 parts or 6 parts. And whatever parts it's getting, it always has to be divided by this 3 mass. So you're going to understand if it gave all 10, let's say if it banged into it and stopped moving, so B just stops, and A gets all 10 of the momentum, it'll be in the form of the 3 velocities. So you have to divide the 10 by 3 mass, and then you can say, okay, well the velocity will increase by 3.3. So it's 3.3, and so the total velocity is 5.3. And it will have now 16 momentums. So everything is quite rational. So he talks about, yes, B can hit, so I'll read that part. B can hit with a little bit, B can hit and exchange a lot. And then we get into the tricky part where he theorizes about a reflection. Now, there's no way we could do this experiment. So even this 10, so let's just say we stop at 10, and we say that B is going to give all its energy to A. We can't do that experiment. We can make B stick to A, or we can make B partially push A, and now they're both moving in the same direction. But we can't make B stop and A go. So we don't have any experimental way to make B stop and A go. There's no device that'll do that. Now spring helps, but it won't make that happen. So right there we know this isn't, Newton's not talking about some actual experiment he did where he made the energy in B totally go into the A object and move the A object. That we don't have that experiment. All right. So back to the text. All right. All right. All right, 6 to 10. Suppose then that their motions be 6 parts and 10 parts, and that the sum will be 16 parts. Therefore, upon the meeting of the bodies, okay, so B is now going to catch up to A. If A acquires 3, 4, or 5 parts of motion, okay, and so the motion is his word for momentum. All right, so that's the tricky part. All right, he says velocity when he means velocity, and he says motion when he means momentum. All right, so it's 5 parts of motion, 3, 4, or 5 parts of motion. That means 5 parts of this, the P part. All right, and it goes over here. Then you're just saying, okay, this one will get 1.7 extra velocity, but you always have to divide by the 3 mass. So any loss of velocity here has to be divided by the 3 to go into here. It's going to be 1/3 of the velocity and conserve the momentum. All right. For 6 parts, okay. If A acquires 3 through 5 parts of motion, B will lose as many, and therefore after reflection, A will proceed with 9, 10, or 11 parts. So it'll just be a momentum exchange. Now when he says 9, 10, or 11 parts, he doesn't mean parts of velocity, he means parts of momentum. So again, when you're exchanging from the small fast object, the small object, to the big object, you have to divide the velocity by the mass. And B with 6, 7, or 5 parts. The sum remaining always 16 parts as before. So clearly he's arguing you must conserve the momentum. All right. If body A acquire 9, 10, 11, or 12 parts of motion, so the 11, 12 is the part that everything goes a little screwy because he's imagining motion in the opposite direction now. All right, but the 9, 10 parts, it's still quite rational. So let's just deal with that. Parts of motion, and therefore the meeting proceed with 15, 16, 17, or 18 parts. So he's basically speculating that if B hits and goes the opposite direction, you have to account for it going in the opposite direction. And that means that A has to have 18 parts. And again, you have to figure out that the parts have to go through the conversion. So what is a 2 parts to this is 6 parts to this in velocity. Two parts of momentum here is 6 parts of velocity here. All right. And 6 parts of momentum. Okay, so let's just get to that part because it's, it does get quite screwy. So this is the, I still can't make perfect sense out of what he's saying. If body B losing so many parts as A has got, will either proceed with one part. So body B is the slower one, right? It's saying it gave away 9. It's still going to have the 1 left. So it can give away 9 of its momentums. And 9 of its momentums will be something like 2.7 velocity. It gives this. Add to this. So you always have to do this velocity conversion from the momentums because this is 3 times heavier. All right. All right, so losing 1 part, having lost 9, okay, so we're saying it's down to 1, and then because it's a 1 mass, that means 1 velocity. Our stop and remain at rest, so he's saying, well, if it stops, it means it gave away all of its momentum, okay, having lost its whole progressive motion of 10 parts, or it will go back with 1 part. So here he's saying if it goes in the opposite direction with 1 part, all right. Now obviously this is an experiment you could do, okay? I can't do that. I can't hit something and move it and move the object in the opposite direction. So we know we can't do that. Having not only lost its whole motion, but if I may say, so he puts that here, if I may so say, so he's arguing about something that he's making it up. I mean, that's what that little thing there, if I may so say, even though it's not reasonable, he's saying if it did happen, this would be the consequence. 1 part more, it will go back with 2 parts. Or it will go back with 2 parts because a progressive motion of 12 parts is taken off. So that's just the 12 is the 6 off of the, you have to minus for every part, you have to do the divide by 3, the 6th thing. Now 12 parts would, so I can't make sense out of 12 parts taken off. So that I can't figure out how we get a 12. Because 16 minus 4 is 12. And where would the 4 come from? So yeah, that one, so somebody else is going to have to explain that. Or I'm going to have to think about it some more because I can't figure that part out. And so the sum of the conspiring motions, 15 minus 1. So that one makes sense, right? The 15 minus 1 you can get. The 16 plus 0 you can get. Okay, there's no motion in the other object, so that's 0. So you still have a positive motion here, and you have 15. So that can figure out. And then you can figure out where, okay, you've given, it has 0 here and you have 16 in this. So that makes sense. And the difference of the contrary, there's a broken word here, option 17 minus 1. So that would be the part where he says, if you're going to be able to go minus here, this one has to have a positive force this way. So for some reason, it has to now have this increase because it's creating a motion in the opposite direction. But he doesn't account for that in any way, where that came from. And 18 minus 2 will always equal 16. So again, he's asserting it's 16 total momentum. So no matter what you did here, you have to have the same 16 total. So there's no confusion about his argument that it always will equal to 16. As they were before the meeting and reflection of the bodies. But the motions being known with which the bodies proceed after reflection, the velocity of either will also be known. So again, now he's just saying, okay, we know the quantity of motion, we know what the velocity conversion will be because it's just about the mass. But he doesn't say that. Anyway, as the motion after is the motion before. So again, he's saying the momentum before is the momentum after. So motion and velocity aren't the same thing. Motion is momentum. As in the last case where the motion of the body A was of 6 parts before reflection, that's what it says, and is 18 parts after, which doesn't make much sense, but we're saying that somehow A pushes B away from it. Okay. And when it pushes B away from it, it gains 2 parts of momentum if it gave A 2 parts. Okay, and the velocity, it can't gain 2 parts. It gains 6 momentums. Okay, the velocity is 1/3 of the velocity it gives. So it gains 2/3 of a velocity to give the other object a whole velocity. 1/3 was 2 parts before reflection. The velocity after reflection will be found to be 6 parts. So he's just saying that obviously if this goes away with 2 parts, it's 6 parts that this in this form. So if it's in the 3 mass, it's 6 parts of velocity. But yeah, he's really, by saying as the 6 parts of motion before is 18 after. So he's saying six parts of motion here in the 3 mass with the same velocity would be 18 parts. And vice versa. If you have 18 parts here, you're going to end up with, it would convert to a velocity, okay, that would, if you have 6 parts and you give this, well, never mind. 6 goes into 18 3 times. That's the giveaway, okay. So our 2 of the velocity before reflection to 6 after. So this has the 2 velocity to start with. And the argument is that if I reverse it and gave this is giving back 2 parts. If this gives back 2 parts, it'll end up being 6 here. 6 parts. Because of the mass difference. Alright, so let's see, 6 parts. By saying as 6 parts of motion before is 18 after, so are 2 parts of velocity before reflection to 6 parts after. So he's just basically saying, look, 2 parts here, 6 parts here equals 2 velocity here. So 6 velocity here is 2 velocity here, and 2 velocity here is 6 velocity here. So if you're going to convert it back because of the mass difference. So that's all he's saying there. So there's really nothing where he's saying you can make more momentum, that you can make an object go 18 and you can make the other object go 2. There's nowhere where he's saying that's possible. All right, he's just using an argument where what if, as I might say, what if it did bounce? And you'd still have to account for that bounce and the fact that this must gain motion in this direction. If you're going to give something motion in that direction, there has to be an equal improvement in this one's condition. So yes, you started with a total of 16, and what you're saying though is there's this point where these two come in contact and then something pushes them apart. And that something that pushes this one this way has to push the 18 this way. So if you're going to have 2 going this way, you have to have 2 going that way. And then it gets kind of confusing when he converts it into velocities. But he's not saying what they say. He's not saying anything like the 1 mass has 100 momentum. It crashes into the 3 mass and gives it 150 momentums. He's not saying that at all. Okay. So he's not a Leibnizian. The rest of it is he starts going on to 3-dimensional, so it's just it's the same argument in 3 dimensions. And so he's still arguing for conservation of the total momentum in the system. He's just arguing that it's a lot more complicated when you start changing the angles at which something hits something. Glancing blows have a whole different set of rules. All right, so that's probably enough of that. So we'll go back to the comment and such. All right, I guess I'll just read it and then I'll respond to it as a whole comment. With regards to the bulletproof spring, okay, and I did say a bulletproof in the sense that it's not going to get destroyed by the process. The point is to make it somehow elastic. So I will elaborate on that argument. Short answer is the kinetic energy is not conserved because in an inelastic collision, whoever could possibly think kinetic energy can be conserved while pressing a stiff spring until red hot. So that's not the argument. The argument is having a spring that can work, not one that fails. So you're not even paying any attention to the argument. I think that any object stretched from their equilibrium will produce heat and loss of energy. Yes, everything has a loss, okay? A regular spring gets hot. Everything does. The argument is that in most cases, it's a minor amount of energy you're losing. It's like a battery. It'll store energy, but it doesn't do it perfectly. So you lose a little bit. I mean, your car battery's leaking, 1% of its energy every day, such as a rubber band heated when stretched, right? But the argument is that heat is a tiny percentage of the energy that went into stretching the rubber band, so you can discount those losses as being trivial. I do find it odd that momentum is conserved despite this fact. So again, I don't know what fact you're even talking about. Intuitively, I would think that energy is represented by movement in objects. Well, I would argue, whether you think it intuitively, I would think every single physical event that takes place around us demonstrates that to be the truth. There's all kinds of evidence that momentum is conserved, and then I could use all these space arguments and say conservation of momentum is what landed man on the moon, not mv squared. And its loss in movement would equate to its transformation or storage. Yes, obviously if you're storing it or you're creating heat, you have to use momentum. So I've repeated that argument over and over again. There's no such thing as deformation or heat or sound or vibrations without using something's momentum. You can't make any of those things without using energy from some source. But I am unable to contend kinetic energy. It kind of works fine. So I hated that last line. It's just such a steaming pile of absolute bullshit. I mean, people who do that kind of thing I'd almost argue you should be shot, because it's such a lie, that this theory works. I mean, it doesn't come close to working. And, I know you haven't been here for all, whoops, wrong button. But this argument has been made over and over and over and over and over and over again. I mean, this classic simple example, and it's a proven experiment. Okay, this one's well proven. 5-ton, 5 mass objects. You just add another 5 mass to it in a very discrete way. You end up with a 10 mass, okay, with 1/2 the initial velocity here. Okay, and you lose 1/2 of the kinetic energy. You minus, okay, I should write it in red, minus, minus 1/2 the KE is lost. No matter how gracefully you do the experiment, you lose half the kinetic energy in something this simple. And obviously the momentum is almost completely conserved. So a 99%, I've seen the experiment where it really is 99% conserved, the momentum. You lose such a tiny, tiny bit. It's just a little tiny bit less than 1/2 the speed. So beautiful conservation. Because what you're really doing here is, especially if you drop the mass, you're not using any of this energy. The motion that way isn't being used by dropping something this way. So you can do the experiment really gracefully. Anyway, so what's how is that? It works fine. How is this? It works fine. It doesn't work at all. I mean, half the kinetic energy every single time I want to do an experiment where I take the energy from a light object and put it into a heavy object, I lose half the kinetic energy, and you're telling me that's a working fine theory? All right, and so then on to the bullet. So what if, I'll rephrase the question, because he cheated it by saying, well, I'm not going to pay any attention to the fact that you said, what if we could make a spring that could do this? So let's make it a rubber bullet instead, okay? So we'll make it a rubber bullet, and we'll knock its velocity down quite a bit. So maybe it's only going, let's make it go like 500 miles an hour. Okay, so it's not too fast. All right, and now we hit the ballistic pendulum, okay, with a steel little plate in front of it instead of clay. So now the bullet can bounce off of it. So instead of penetrating and absorb, losing some energy to heat, and deformation of the clay, you obviously lose some energy in the wrong directions. But the whole idea is you capture 95%, let's say, of the momentum is captured by the ballistic pendulum of the bullet, because they couldn't get accurate velocity numbers if that weren't true. I mean, the fact is they measure the velocity of the bullet both ways. They can measure it by the pendulum, the momentum, or they can measure it visually, through other mechanisms to measure the timing of the distance, how far it traveled. But anyway, so they've already verified this works. The ballistic pendulum conserves the momentum substantially. All right, so it does work as a device. And your claim is that if I did this rubber bullet experiment, all right, where I first penetrate into the clay and absorb its momentum that way, and then I do the experiment a second time, all right, where I just plow it into the surface and allow the rubber bullet to bounce, you're saying this pendulum will have more Ke than this pendulum. Okay, so this will be Ke plus Ke here. I'll get my conservation of kinetic energy here, and I won't get it here because I got this reflection. So because bullet reflects, bounces off with energy going this direction, that somehow I got more energy into the ballistic pendulum. And I'll say, yeah, the day you show me that, okay? But anyway, that's the real example, is that your theory really can't do it because it's a mathematical problem. Your math says you can't do it. Your math says you can't put energy into big things because they have that squared function. That squared function is always going to force you to lose a tremendous amount of energy because of the velocity. The squared smaller velocity number is going to kill you. So you can't ever theoretically conserve the kinetic energy every single time you try to take energy from a light thing and put it into a heavy thing. And the vice versa problem, every time you try to put from a heavy thing into the light thing, you're going to have to destroy an awful lot of momentum. All right, so, create an awful lot of free momentum, because, yes, this can't do it. Can't create your extra kinetic energy. All right, your extra velocity. So that might be enough. Yeah, I'll just leave it at his subjects and then keep it simple. I do want to describe, like in space, what would happen if you have two velocities. You have something moving this way and you hit it with something going this way, and so now it's moving this way. And the fact is that way is faster than the original way. I mean, this line is a shorter line than this diagonal line. And then if you move that in 3 dimensions, you get even a little bit longer line. So the fact is you can increase something's velocity by hitting it tangentially. And every vector can be broken down into its, into 3-dimensional. You can do your 3-dimensional analysis of any single vector in a direction. You can cut it into how much is it going this way and how much is it going this way and how much, the 3-dimensional thing. And so you can always convert it into 3 combined velocities. But anyway, that's sort of an interesting subject. But anyway, let's finish this one first. Okay, so we'll leave it at that and such. I appreciate your comment. Thank you. But, this is just so hard to swallow. Okay, but I am unable to contend kinetic energy. It kind of works fine. It's just amazing that you can say that in the face of the fact that it doesn't work at all. It really doesn't work. 4 times the fuel to go twice as fast. 9 times the fuel to go 3 times as fast. 16 times the fuel to go 4 times as fast. 25 times 100 times the fuel to go 10 times as fast. You call that working fine? That you really believe that's the truth? I don't think you think that's the truth. Explain it. If you do, show me the experiments that convince you, okay, that it's, takes 4 times the gas to go twice as fast. Show me. All right, now it's enough.